Hello, my name's Randy. In this Treehouse workshop, we're going to code a simple HTML5 game. It'll run in a browser on a desktop computer, but also on a touch device like a smartphone or a tablet. Let me give you a quick look at how the game will look when we're finished. It has Mike the Frog, and he's moving around this maze here trying to collect these badges for HTML, CSS, and JavaScript. Alright, so let's get started. I broke the workshop into 3 sections: code, HTML5, and games. Of course, it'll be easiest to talk about them in the reverse order. We'll talk about games first, why they're fun, why people play them, and how they can help us in our everyday life. Then we'll spend some time talking about HTML5, what are the new features, and why do people talk about games in the context of HTML5. And then we'll walk through building this sample game line by line through all the code. Ready to get started? Alright, well let's start by talking about games generally. Personally, I love games, and odds are you probably do too. There's a few reasons for that. First, games are fun. That might seem obvious, and you might think of games and fun as a waste of time, but actually, we take fun here at Treehouse pretty seriously. It's a very important part of life. If you're interested in learning more about fun and why fun is so important, I would recommend this book, A Theory of Fun. It came out about 9 years ago. It gives you a good idea of why fun is important, what it does for you, why people are so interested in engaging in fun. Another reason that I think games are important is that games are everywhere. And I'm not just talking about gamification either, where you try to add games onto things that aren't really games. Games really are everywhere. There's this dry academic book called Homo Ludens, which is Latin for man the player or man the gamer, in which this academic studied the effects of play in culture. And he argues that everything that we do as humans, everything that's important to us from a cultural perspective, is really driven by a sense of play and a sense of games. He's not just studying games inserted into culture, but he's studying how everything that we do is driven by a sense of play. You probably don't want to read this whole book, but it would be worth checking out the Wikipedia article to get a good feel of how culture and play work together. Another reason I think games are important is because games exercise the brain, and not just the math part of your brain, but I want to read this quote to you from the Life Optimizer blog. Play engages the prefrontal cortex, responsible for your highest level cognitive functions, including self-knowledge, memory, mental imagery, and incentive and reward processing. It turns out that most of the things that we value as human beings in our brains are triggered when we're at play. This blog post recommends a number of games you can play to help trigger some of those things, games like Scrabble, chess, or even Sudoku. And there's a lot of apps that you can play that will help kind of trigger a lot of these things in your brain. Games like Cut the Rope, Bad Piggies, Where's My Parry. And if you are interested in chess, there's chess.com, which is a great way to play chess asynchronously online with people. Not only that, games are also practice for the real world. When you play a game, you do learn a lot of the things that are really important for being successful in life. Things like planning ahead, fourth dimensional thinking, constraint management, resource management, and those kinds of things. I would recommend this blog post, 7 TED Talks on Gaming, to get a better idea of how this works, including this one here, Gaming Can Make a Better World. As you can tell, a lot of people like games, and I think games are very important. Let's next talk about HTML5. HTML5 is a pretty hot buzzword right now, and I should warn you that this section of the talk will be filled with buzzwords. If you have your buzzword bingo card handy, go ahead and get it out. For each buzzword I say, check off the square and see if you can get 5 in a row for a bingo. My goal is to not use so many buzzwords that you would get a bingo, though. When people talk about HTML5, they're often talking about a lot of different things, and usually what they mean is enhanced functionality in the browser. There is an HTML5 spec that has some new elements like header and section and some other things that we'll look at, but there's also a lot of technologies that are related to the browser, related to HTML, that people often lump into HTML5. So when I say we're going to code an HTML5 game, I really mean a browser-based game that runs without any proprietary extensions. The first piece of technology I want to look at is the canvas. This is actually a new HTML5 tag. A canvas is a blank HTML element that you can draw on with JavaScript. So you can create any kinds of shapes like lines or circles, or you can add imagery and then you can use JavaScript to animate it around. When people talk about HTML5 games, the main thing they're often talking about is a canvas tag, so that you can create your whole game inside of a canvas with JavaScript. The next thing that people often talk about with HTML5 games is WebGL. This is a graphics library that's open source and can run in some browsers that support it. Not every browser today supports WebGL, but it gives you a way to animate graphics in three-dimensional space in a way that takes advantage of the computer's hardware processor for rendering graphics. Many browsers will support WebGL right now, but you'll need to make sure that the browser you're targeting does before you can use it. I have a great blog post about why use WebGL that I'll link to. Not every HTML5 game needs it, especially games that are two-dimensional. The game we're going to build doesn't take advantage of WebGL, but this is one of the technologies that people often talk about in terms of HTML5 in games. Another piece of technology that people talk about in terms of HTML5 games are WebSockets. This is a way that a browser can talk to a server through a WebSocket directly, not through the typical HTTP request and response paradigm. So you might be familiar with AJAX, allowing a web page to talk to the browser, but that's asynchronous. It sends off the request, waits for a response, and you can try to make it look like it was synchronous, but it's really a request and a response that are separate. With WebSockets, you can really open up a connection directly to the server, and they can send data back and forth. This is really important for online games or games where you're playing with multiplayers or any kind of application where you need real-time feedback like a chat client. WebSockets provide a great way to do that. We won't be using WebSockets in our game. It's a simple 2D game that runs just in your browser. There's not going to be multiple players running around the maze. But WebSockets are one of the important pieces of why you can use the browser for a game. And another new HTML5 technology you might hear about is SVG. This is a new graphics format. SVG stands for Scalable Vector Graphics. And instead of the images being pixel-based, like with JPEGs or PNGs, the image contains instructions about different vectors, like draw a circle here from this point, draw a line here. It can be a lot easier for development because they can scale up and down. You can easily change colors just by editing a text file. But it can be tricky with games because it takes the browser a lot of time to redraw each graphic based on the vector instructions. And many times the performance is just not there for the game. There are, of course, some examples of games that use SVGs really well, but they just don't seem like they're there yet for the browser-based games. I'll link to some experiments people have done, just to give you an idea of what people are talking about in terms of HTML5 and SVG. All right, let's next talk about HTML5 and games. The HTML5 Rock site has this quote, "It's official. With HTML5 today, the browser has become a full-fledged gaming platform." That's technically true. You can build games that run in the browser, but the field is still in its early stages, I would say. People are building frameworks to make this easier. People are doing a lot of trial and error with JavaScript to make it work. A great example of that is the Cut the Rope browser-based games. If you go to cuttherope.ie, you can see this game, how it's playing out, all done in the browser. The animations, the mouse, the touch screens, that's all happening in the browser. Now you can play Cut the Rope with an app, and we usually play it with an Android app. But as you can see here from this little demo, the browser can handle a lot of this. What I like about this Cut the Rope example is that it's a great game that plays well in the browser, but they also have a behind-the-scenes blog post you can check out where they talk through all the different things they had to do to get it to work. It gives you a good idea of kind of the state of HTML5 games, how they worked with JavaScript to get it to run, if they chose a framework or not. You can kind of get a feel for what it's like to work in the HTML5 gaming field right now. All right, with all that behind us, all the talk of games and theory, HTML5, and the state of HTML5 games, let's get in and write some code. Now, an HTML5 game looks very much like a web page as far as its structure goes. We have an HTML file, a CSS file, and a JavaScript file. The HTML file will primarily have just a canvas, and this is where we will draw the game with JavaScript. In our first example that we're going to work with, there will be a CSS file with a little bit of styling, but not very much. Almost all the guts of the project is in the JavaScript file. This is where all the code will be drawn, all the graphics will be drawn, all the code will be written, all the logic for the game will be handled. But just to show you, an HTML file would look something very simple like this. If you've worked with web pages at all, this shouldn't look scary. The one thing that's new is the canvas tag. So it's just a regular old HTML tag. There you can see it. I've linked to the style sheet, and I've included the JavaScript file. The CSS file, all it really does is styles the background of the body and displays the canvas so that it's centered. With the HTML file and the CSS file in place, if we were to look at it in the browser, our game would look like this. It's not really a game yet, technically. It's just a white box on a gray background, but it is HTML5, technically, because that canvas element is there. So let's go ahead and get started working with the canvas element. In that JavaScript file, we're going to first call the document.getElementById method to get the canvas element. So this, if you've done any kind of selection with jQuery or JavaScript, we're going to select that canvas element out of the page. And you don't actually draw on the canvas directly. The canvas has what's known as a context. So we'll go ahead and call the canvas's getContext method to get that context in a variable. And we'll call the 2D context. So this is a two-dimensional context where we can draw on the canvas. You can do the 3D. That's if the browser supports WebGL. The WebGL will come in there at the 3D context for the canvas. We're going to just pull in the 2D context. Now our game is going to have that Mike the Frog image, so we'll go ahead and create an image object in JavaScript here. We'll set its source attribute to just a local path here, or a relative path, images/MikeTheFrog.png. Now we don't want our game to start until that image is loaded. The common way to do that is to add an event listener to the image, so once it's loaded, then we'll call our init function. If you've worked with jQuery's document_ready method, you've probably seen that before. So you don't want your jQuery to execute until the page is ready, until it's fully loaded. And this is a common approach here. If we had a lot of images in this simple file first, you might see it done as a sprite sheet, so one image file with a lot of different graphics in it, and you'd want to wait until that had loaded before you started your game. So once the game starts, we're going to call that init method. One thing I should note here is that we're going to want to animate this, and browsers haven't been very good at animation in the past. This is another new feature in modern browsers, this ability to tap into the request animation frame object. This is a new browser technology to allow you to modify things in each frame or according to the frame rate. Before you could access this request animation frame, you'd have to do it with JavaScript timeouts. So this little block of code, what it does is it creates a variable that will use whatever the browser's best method is for requesting the animation frame. It has fallbacks for different prefixes, and then eventually a fallback to JavaScript where it's setting a timeout. Once you have this in place, then you can set up your init method. So what we want to happen is when the init method runs, it will set on the request animation frame, which will tell the browser the next time you draw the frame, I want you to call this update method. In the update method, what we're going to set is we're going to tell the browser the next time you draw a frame, we want you to call the update method again. You'll notice this creates a recursive pattern, so the browser will call the update method, which will redraw a frame of the game, then it will call that function again. And this is pretty common game logic. You'll have a function that initializes the game, and then you'll have an update method or function that you call on an ongoing basis. Inside that update method, you would move the characters around, you'd check for collisions with walls or with the collectible objects like badges. All right, so inside our update method, the first thing I want to do is draw a rectangle for one of the outer walls. The canvas context has a fill rectangle method. You pass in 4 parameters, the height and the width and the x and y coordinates of the top left corner, as well as the color that you want to draw. So with this command in place, we'll draw a rectangle, a black rectangle over there on the left side of the wall. To do the same thing all the way around, we just call that method more times. So these coordinates will all set up different walls around the edges. In the browser now, this would look like this. It's a very simple maze. We're calling the context.fillRectangle method 5 different times to draw those 5 different walls. Let's put the frog in the game. This will be an image, so we can call the drawImage method on the context. We pass in the image object we want to use. And then there's 4 other arguments we'll pass in, the height and the width and the x and y coordinate where the image should be drawn. If you are using a sprite sheet with lots of images in it, you can send in 4 more arguments that will tell it what coordinates from the sprite sheet you want to pull out. Right now, though, I've just got one image with just the frog in it. Now, instead of setting the x and y variables as hard-coded values of 65 and 65, let's use a variable for these. The frog is going to move, so his x and y coordinates are going to change. So I've created here an x and a y coordinate, set them each equal to 65, And then when I call the drawImage method, I pass in those two variables. At this point, our game looks like this. It's starting to come along. It's starting to look like a game. There's a frog in a maze. But it's not very exciting yet until we get the frog moving. So let's modify our update method to move the frog. So just as a simple example, inside the update method, we'll set his y coordinate to be increased by 3. When we do that, when I refresh in the browser, you'll see it moves the frog like this. Well, that's not quite what we had in mind, but you can see the frog moved 3 pixels every frame. And computers are shooting for 60 frames a second, so it's about 120 pixels down every second. We really need to clear the frog off of there, though, so that he's not reduplicated in like a jet stream. We don't want to duplicate the frog each frame. We want to clear him off and draw him again. We can call the context clear rectangle method there, pass in the area we want to clear, and then each frame it will redraw the frog. I've actually set it up right here to just clear the whole screen and draw everything again. If you had a very large game with a large world and it scrolled and scrolled and scrolled with a big long map, you wouldn't want to do this every time, clear off the whole frame and draw it again. You'd have to get really smart about which pieces of the map you could clear off. But our game is pretty small, only 400 pixels by 400 pixels, so we'll just clear the whole rectangle off. Now, when we refresh, you'll see the frog moves down. Of course, he goes right out of the map, which isn't what we want either. So we'll need to start checking for obstacles, and we'll need to modify our logic quite a bit. So right now, in our little game logic model here, we have the initialize function and the update function. In our update function, the only thing that we're doing right now is moving the frog. Typically, when you'll see game logic discussed, there's one more element here called render, and this is where it actually does the drawing. So in the update method, you'll set all of the variables, you'll move the frog from one spot to another, you'll check for walls and badges, and then the program will re-render the whole image. If we were to break down what we're doing in each of those 3 pieces right now, in the initialize, we're placing the frog and we're placing the obstacles, and then in the update method, we're moving the frog, and then we're re-rendering the interface. We'll want to do a bit more, so when we initialize, we'll also want to bind some JavaScript events. This is for capturing touches or key presses. Right now, the frog just moves on his own, and we'll want to start him moving with a key press. We'll also want to place some badges. It's not really much of a game until he can do something, like go around and collect badges or maybe find an exit. But ours is a collection game. He's trying to collect all these badges. And then in the update, when we've got walls and badges, we'll also have to check his movement. Can he move to the next spot? Is he moving? Is there a wall in front of him? If not, then we can move him. And then we'll want to check if after he moves, there's a badge there for him to collect. And then we'll want to re-render. Of course, the other thing we should probably check for is if there's a victory condition. So we're going to have 3 badges in our maze, and we'll want to check after each time he moves if there are badges, and then if he's collected all of the badges or not, so we can end the game. All right, so just to refresh, this is what our game is going to look like when we're done. We'll have this controller here where we can press it to move the frog. We'll have the maze walls, and we'll have the badges in place. We could keep going building this game from scratch, but I think at this point it would make sense to switch to using a game framework. There are a lot of JavaScript frameworks out there for building games, and new ones seem to be coming out all the time. The one we're going to use is called Lime.js. We're going to use it for a number of reasons. First, it's open source and free, so you can just download the code from GitHub and get started. Second, it uses DOM or Canvas elements for rendering the game, so you don't have to rely on newer browsers that use Canvas only. You can actually use HTML5 for some of the game attributes, using divs and images for rendering the game. The third attribute, it's built on Google Closure. So this is a library that runs and gives you a number of tools that make JavaScript easier to work with. It has dependency management and some minification built in. It doesn't require Python on the server where it runs, just needs it on your development environment. If you've worked with a preprocessor for CSS like Sass, you'll probably be familiar with this dependency. Sass requires Ruby to be installed where you're developing it so it can compress, modify, and combine all your CSS files, but you don't have to have Ruby running on your production site. Same is true with Lime.js and Python. Once you have Lime.js installed, you'll only need to run a command like this to create a new game. Just tell it to create the game and give it a name. It'll create an HTML file and a JavaScript file in the folders where you need it to run. The HTML file it creates will look something like this. It includes the Clojure library's base file as well as a JavaScript file for your specific game. I added a little CSS just to change the styling for the background. It creates that treehouse.js file here with the few different things you need from Clojure to get it up and running. But the main bulk of the game is this start function on the treehouse object, which will control the logic for the game. When you first create it, it'll have a lot of code in there for a sample game. I just went ahead and cleared that out to start with a fresh base here. As you start the game, the first thing that you'll need is what's known as a director. So using Google Clojure's dependency management, you include the Lime director file, and you create the Lime object and the director object in your code. The director in the game is kind of the brains, like a director of a movie. It controls what objects exist, where they go, manages around shuffling between scenes. So all games in Lime start with a director. And there's a few settings on the director that you can set. So you can call this make mobile web app capable, and you can tell it to not display the frames per second. Those can be useful for development, but this will really get your game to where it's ready to go for real, and it'll work on a mobile touchscreen device. Lime.js games think in terms of scenes. Our game's only going to have one scene. Games might have more. You might have a start and an end screen, or multiple levels that are all different screens. But for simplicity, our game's just going to have this one scene. Now, to create a scene object, you'll have to include the Lime scene file, and then you can go ahead and create a new scene. I mentioned when I first talked about Lime that you can use canvas or DOM elements. And what's nice is you can code your whole game and then make a decision about it at the end. You just check this line here. You tell it you want it to render using canvas, or you can change that to render using DOM. So you might want to give it a try in whatever real environments you want it to run and see if you want to switch it to canvas or DOM. When I tested this game, I found that it does actually run better with the DOM elements in place over the canvas on some touchscreen devices. So at the end of this project, I'll switch it back over to DOM. But this is how you'd set it to canvas. And then to get the scene, the initial scene that we just created, loaded up, we call the director's replace scene method, and it'll take the scene we just created and load it up. In the browser, that'll look like this. So we've got our file in place. My CSS I wrote sets the background to gray, and then it includes our scene. Now this did put a canvas element on the page. You can't see it because it's transparent, but it's ready to go. We've got another HTML file right here ready to go. So I'll break my start function up into two pieces, the one there at the top where we define all of the objects, and then the one down at the bottom where we actually set the scene. Setting the scene has to be the last thing that you do, and we'll go ahead and put all of our objects onto the scene before we do that. We're ready to start adding objects, and these are known in Lime as sprites. If you've worked with CSS, you've probably heard of sprites before. You can create games where they have a sprite sheet, and every object inside the sheet is an image. But it doesn't have to be that way. The term originally comes from gaming, and the idea is that a sprite is one of the objects in the sheet. So each object in our game, the frog, the walls, the badges, are all going to be known in Lime as sprites. The first sprite we'll create is just the game background. This will be a background where we can put all the other things on there. So I'm creating it here. In Lime, the objects all chain together just like they do in jQuery, if you've ever worked with that. So you can just keep calling methods one after the other. So we'll create our game background. It'll be a sprite. We'll set its size. We'll set its position, we'll set its fill, and we'll set its anchor point. We'll set the anchor point at the top left corner with 0, 0. That just means whenever we talk about the position of the sprite, what position inside of the sprite is that related to? So by saying 0, 0 here, we're going to position that top left corner into the top left corner of the canvas. After that, we'll just need to append the game background onto the scene to get it ready to go. The next sprite I want to create is the controller, that analog stick that you can tap to move the frog up or down. This will be another sprite. We'll set its size and position and anchor point just like before, and we'll call the append child method on the scene to place the analog stick onto the scene. In the browser now, that looks like this. Now you might be wondering why there are gray bars at the top and bottom if we set our background to be in the top left corner. Well, with Lime.js, even though we've specified absolute sizes for everything, it's still going to try to scale it to fit in the browser that it's running on, whether that's on a small screen device or on a big screen device like the computer. So based on the aspect ratio, it will add bars at the top and the bottom, or on the left and the right as necessary. If I were to open up the inspector here, you would see it would actually scrunch everything up and it would put the gray bars on the left and the right. Now, when I really develop games, usually what I have open is not the inspector down below, but I have the JavaScript console opened up on the right. So I can see, I can debug, I can test with the console over there, and the game then will scrunch down to fit inside the device. The next sprites I want to add are actually not going to be visible. They're going to be the touch areas where you can touch the controller. So I'm going to create a button up, right, down, and left sprite. We'll put them on the controller on top. They'll be transparent though, so you won't be able to see that they're there, but you'll be able to interact with them. So again, calling the exact same methods, I'm going to create these 4 new sprites, and I'm going to append them into the scene. We'll bind events to those in a minute, but let's first get the frog in place. Now the frog is going to be a new kind of object. It will be a sprite at its core, but it's going to have some extra features related to movement. So I'm going to create a new class, or a new kind of object, a frog object. This is the code that you need to create a new kind of object in Lime.js. The very top line will tell Google Closure to manage all the right JavaScript dependencies and get the JavaScript include files included in all the right places. The second line includes the base sprite file. And then the last line tells Google Closure that this frog object is going to extend the sprite object. When we create a new frog object, we'll set up some base parameters. We'll set the size. All our frogs will have the same size, even though a sprite element could have different sizes. We'll also set a fill, so we'll set the frog to use our frog image. We'll use these properties. Is he moving? Which direction is he moving? And what's the speed at which he's moving? These are the initial values for the properties. He won't be moving when he starts. He'll be facing north. But as people use the controller, he'll start moving. We can change the direction that he moves. Now back in our main treehouse JavaScript file, we'll need to include that new frog file so that our main program can make a frog object, just like it can make a director, a scene, and a sprite. Now, one word of caution, when you create a new kind of object, like a frog object, you'll want to run this command at the command line so that it will update. JavaScript doesn't really manage dependencies very well, and that's what Google Closure helps with. But you'll have to run this script inside of Lime to get Google Closure to update all of those dependencies. There's been plenty of times where I've been writing a new kind of object and I just can't get my JavaScript to work. Well, it's because I'm not running Lime's update method here. So word of caution there. Be sure to do that when you're using Lime.js. Now for the directions I'm going to use for constants. JavaScript doesn't really have constants, but there is this convention that if you write a variable name in all capital letters, you can use it like a constant, and you just have to stick with that. So we're going to create numbers for each of the directions, north, south, east, and west. And then throughout the rest of our code, we can check if he's moving north, and north will be a variable that corresponds to 1. Those numbers are arbitrary. It's just key that you always call them by that exact same name. Now we can go down into our code, and we can create a new frog. And just like we did with sprites, we can append the frog into the scene. And we don't have to set his size or his image because that's built into the core nature of what it means to be a frog here. We've put the image and the size into the frog object itself, and now we can append the frog to the scene. Looking again at the game logic, we'll see Lime.js by default will initialize and then render, and it will handle all of that for us. So it will handle the rendering. We don't have to re-render the screen. We don't have to set up the animation frame. We don't have to set JavaScript timeouts. Lime.js will handle all of that for us. One more thing we should do in our initialize function is we should add the walls and the badges. So what I've done here is I've created an array that's part of our main treehouse object for walls, and I've created an array for badges. The code for setting all those up is a little tricky, so I wanted to walk you through how I would do it. I created 2 methods, one for create walls and one for create badges that I can call, just to keep my main program code uncluttered. Down in the create walls, what I did first was I created an array of coordinates. So you can see I created 2 sets of coordinates just to get started. This will be the top left coordinate, the 0, 0, and then the height and the width of the wall. And then I have a loop that runs through all of the coordinates and calls the main Lime.js code to create a sprite there. Again, I'm setting the anchor points, positions, and all those normal things. And then I'm going to append that new wall object to my main array of walls with the push command. Now I realized very quickly that I wanted to be able to scale this up and down without too much trouble as I was testing the different variables. So I created a scaling variable. I called it t. Then I used that scaling variable when I set up these coordinates. That way if I decided I wanted the walls to be thinner or thicker, I could just change this variable. So I called this t for thickness, and then I multiplied the different coordinates by that t variable. So the first wall would be 35 times whatever the thickness was. That's how long the wall would be. The second one would be 26 times this tall. Then I added all the other walls, just like this, building out my array. And you can see that I used that t function throughout. That way I can easily change it up and down depending on how wide I want the maze to be. That's just a nice little trick. I did the same thing for badges. That way I could make the walls a little thinner and the badges would all still be placed correctly. So I have a similar function like this that works with badges and badge coordinates and badge names and badge images. And then back in the main program, I loop through the array of walls and append them to the scene. I also loop through the array of badges and append them to the scene. With all that in place, we now have our game set up. We now need to set up the game so that the player can interact with the controller. We'll start by binding an event. Google Closure comes with some nice methods that help with binding events to these sprites. We can set up a new event listener that will listen for the button up sprite to have a mouse down or a touch start event. And when that happens, we can call a method start movement on the frog. We'll pass in a parameter of north because if someone presses the up button, we want it to start the frog moving north. Over on our frog now, let's code the start movement method. It will receive a direction. It will start the frog moving, so he'll change the is moving property of the frog to true, and it will change his direction to correspond to whatever direction gets passed in. We can then bind similar events to the right button, the left button, and the down button, setting them to get the frog moving east, south, or west, depending on which direction is required. We're now ready to code the update portion of the game logic. Lime.js handles that with their schedule manager. Again, we don't have to do anything for the rendering. Lime.js handles that automatically, and with the schedule manager, we can inject code that should run when it's updated. To do this, we can add an event into the schedule. When the schedule is run, this will be every frame, every time this is run, we can call a new method on the frog called check movement. Now the schedule method will receive one parameter. Now any function called inside the schedule manager will receive a variable called dt, which stands for delta time. This is asking how much time has elapsed since the last time I was called. This way, if the computer's running a little bit slower than 60 frames a second, the schedule manager can adjust for that so that you're not going to see the frog lagging or jumping ahead. The dt variable will allow you to scale it appropriately so that it looks like a smooth movement, even if there's something running slow on the computer. Now inside this check movement method, what we're going to want to do is check if the frog is moving. He has a property called isMoving. When the game starts, it's false. So even though the update method is going to be called when we first start the game, we don't want him moving until one of the controller buttons is pressed. So we'll check if the frog is moving, and if he is moving, then we'll move him. If he's not moving, then we'll just re-render and go through the loop again. All right, so let's check if the frog is moving. I've got a conditional here that says if frog is moving. Very simple. It checks the value of that property to see if it's true or false. And if it's true, then we'll determine the frog's future position. So we'll check the frog's current position. We'll get that loaded into a variable. So we'll check his current x and his current y coordinate. And then we'll check what direction he's moving. If he's moving north, then his future y coordinate should be a little bit less than it currently is. And the distance that he should be moving should be based on his speed times this delta time. So just like your old physics class, distance equals rate times time. The distance we want to move the frog is related to his speed times the amount of time that has elapsed. So if he's moving north, his future y-coordinate will be a little bit less than his current one. If he's moving east, his future x-coordinate will be a little bit more than his current one, south and west, so on. So doing this, we would calculate what the frog's future x and y coordinates would be if he moved in that direction. All right, so this is the logic for checking movement, which we've already coded. And if we take a look at this in the browser, you'll see that it looks like this. We can click on up to move the frog up. We can click down, left, right. We can click all the different buttons, and the frog will move. Now, we're not checking if he hits a wall or not, so we can go through the different walls, even run right off the map. That's what we'll do next. But right now, we're checking if the frog is moving, and if so, we're moving him. So we have this logic in place. Before we move the frog, we'll want to check if he's hit an obstacle. Well, how do we know whether or not he's hit an obstacle? This is the code that will check if the future position of the frog would hit an obstacle. We can check the future top Y, future bottom Y, future left X, and future right X. These are the 4 corners of the bounding box around the frog. His anchor point is in the middle, so to figure out where his top left corner would be using his size and dividing his width by 2 to figure out that full bounding box of the frog. Then we want to loop through each wall and see if the frog will hit a wall. So we can start here going through the walls array. We want to find the 4 bounding corners of the wall as well. So using something similar, we can figure out his Y position. Now the anchor point of a wall I have in the top left, so you just have to start with the Y coordinate and then add the width or the height accordingly to figure out his bounding box. Then we've got to write a conditional that will check if the frog's future X and future Y coordinates, the bounding box, would collide with a wall. So we're looking at something like this. We're looking at if the frog's right would be right of the wall's left. So we're going to compare those 2 values. Then we're also going to check if his left would be to the left of the wall's right. Then we're also going to check if his top would be above the wall's bottom. And we'll check if the frog's bottom would be below the wall's top. If all of those conditions are true, then we know that the frog's bounding box is overlapping with the wall's bounding box. And we would know that moving the frog to that position would cause a collision. It might take a little bit of time to think through that, but all the different ways that the frog could be positioned around the wall, if all 4 of those conditions are true, then we know the frog is overlapping with the wall. The conditional would look something like this. If his future right X coordinate is greater than the wall's left X coordinate, and if the future left X is less than the wall right, and so on, comparing all 4 of those different values, then we would know that the frog was hitting a wall. Now, if a frog hits a wall, what do we want to do? Well, we want to stop his movement. So we would set the frog to be not moving, and we could just return false right out of here. So the rest of this function is where we actually move the frog and check for badges. But if he's going to stop moving, we can do an early return here. Just return out of that function, return a false, which would mean the frog did not move. And that way he won't move. We'll just stop his movement, and we won't move him to that future X and future Y coordinate. So we've got this basic logic in place. If he does not hit a wall, we'll move him. If he would hit a wall, though, we can stop his movement. So it's not just that we won't move him, we'll stop him from moving. We'll change that isMoving variable to false. Now if we were to look at this in the browser, it would look like this, and we could click on these buttons. We could click up, and when he hits a wall, he would stop. So that update part is being called every time, and it's moving the frog, the delta time times his speed, until he hits a wall. So this is the logic we've got in place so far, but you'll notice when he hit that HTML badge, he didn't collect it, he just went right through that. So the next thing we'll want to check is if the frog is going to hit a badge. Now, we can move the frog first. We don't have to check if he would hit a badge, because when he hits the badge, it's not going to stop his movement like it would with a wall. So we can go ahead and just check his badge. Now, to keep track of this, what we want to know for victory is if he's collected all 3 badges. So we'll set up a variable back up at the top called badges earned equals 0. So this means when you start the game, you have earned no badges. Then back in our movement function, after we've cleared all the walls, we've moved the frog, now we can see if our new position would hit a badge. And the logic is very much the same. We loop through the full array of badges. We figure out if the badge's bounding box and the frog's bounding box would overlap. And if so, we count a collision. But we don't have to do a return here. In fact, we want to loop through and we want to continue to loop through all of the badges to see if he's collected them. And instead of stopping his movement, we want to increase that badges earned. So we want to add 1. And then I'm going to move the position of that current badge that's been hit. I'm going to move it off of the screen. Well, it's still going to be on the screen. It's still going to be on the canvas, but it will be outside of the bounds of the maze. And I'm using the number of badges that have already been earned to determine the position so that as you earn one, they'll kind of stack up in a line. So let me show you how this will work in the browser. So now you can click on the different buttons up and left and over and right. Now when Mike collides with the HTML badge, it will move the badge over there to the right side of the screen. It will increase the number of badges earned by 1. And now when I collect the CSS badge, notice how its position is a little bit to the right of it. It's 50 pixels times the number of badges earned. So as he continues around and earns the JavaScript badge, it's also moved a little bit to the right of that. So looking back at our game logic, what we can see is that if he hits a badge, we'll increase the number of badges earned by 1 and move it off the screen. If he doesn't hit a badge, we'll just keep going and re-render the interface as the frog is moving. The next thing we should check for is a victory condition. Have all 3 badges been earned? So we'll do that here. We'll check if a victory has been achieved. To do that, I'm going to add another method to our scheduler. This will be a check victory method. Now I'm going to put it before the movement. What can be interesting there is we want to check if he's already achieved victory and then check if the frog is moving. Otherwise, you can get into a weird state where you've achieved victory, but you haven't yet re-rendered the screen. So we actually want, back to that diagram, we actually want to check victory at the very beginning, the very first thing we do before we do any of the updates to see if the frog is moved. So it's technically going to happen right after the render, but with Lime.js, you can't really put anything after the render before the update. So we'll put it at the very beginning of the update. So when the game starts, the very first thing it will do is check to see if we've won. Well, of course, we haven't won yet, but there's no harm in checking that first. So I'll have my check victory method here at the beginning. In that check victory method, all I really want to do is check to see if the badges earned is equal to the total number of badges. If so, I'm just going to use a simple JavaScript alert to say, hooray. Now with Lime.js, you could create another scene. That's the outro that says, hey, congratulations, you've won. The cut the rope example I showed earlier does something like that. You go to another scene with some more animation, totaling up your score and all that. And you could totally do that in Lime.js with another scene. You could even end this scene and start another level if you wanted. But we'll just do something simple here with a JavaScript alert. Now after victory has been achieved, should we do anything else? We could just end the game, but I think what I'll do for this case is I'll just go ahead and reset everything. Now once we've got all our code in place, next it's time to package it up and get it all ready to go to production. This is another nice thing about using Lime built on Google Closure is that you can call this minify script. So this will take out all the spaces and all the comments. It will combine all of our JavaScript files into one JavaScript file, which I'll call here treehouse minified. So this will give you the JavaScript version of your game in a very small single JavaScript file. You'll still need to write the HTML that you need to include this JavaScript file, but it'll look very much like that starting file. I've posted a link here on this workshop where you can go and see the finished version of the game and even play it for yourself. Hopefully this workshop gave you a good idea of how to get started coding your first HTML5 game. I'll post some links where you can download this Lime.js code, as well as check out some other frameworks that you might want to try as you get going. This has been another Treehouse Workshop. My name's Randy Hoyt. Thanks for watching.